Hey guys, I'm going to go ahead and make this video for tomorrow, October 6th. Okay, just finished with the first hybrid day with the AA group, and I want to talk just a little bit about first few slides and the direction we're going with that, and that way it'll be easier if you have your headphones. Obviously, my B-ers will be watching this tomorrow, and my A people will give that option too as well. Okay, so we went through the first couple slides there. So 15.1 was just talking about the macroevolution and the main events of evolutionary history and understanding basically the Earth's order of operations, or chapter books, if you want to say that. And basically it's divided into three large eons, and basically same way we'd say maybe centuries and decades and year and month and so on like that. Okay, but each individual one is marked by a large massive or lesser type extinction, something significant, whether the appearance of or the disappearance of a group of organisms, or a major environmental, maybe an ice age or cataclysmic type change within the whole plate tectonics and continental drift type stuff. Okay. So major events in history of life, obviously Precambrian period, these are just some of the more significant ones. I said a little bit to our group, and I'm just going really quick through this because this is just kind of this is just giving you a significant timeline or time frame of events, understanding that these are the various different categories. These are the time frame. Notice it goes from most current, million years ago, all the way down to the Precambrian. And when you look at the origin back here, 4 million years ago, origin of Earth type, oldest known rocks. Okay, until we find something older, okay, this thing can continue to push down, which we call the Precambrian time period. Okay, but each significant level, even was showing you some fiction organisms, whether it be the age of reptiles or the Permian extinction, various different mass extinctions, or the appearance of various fossils. This is just showing you the geographic time scale. But how do we know this? Is what brings us to our main focus for today, is aging of rocks and fossils, which is crucial. Or we a lot of times call it radiometric dating, radioisotope dating, carbon dating. All of those are the same time, or carbon-14 dating. Okay, these are all things that are associated with, means the same thing. Okay, it's basically based on the decay of certain isotopes found on the periodic table. All right, that have a certain time frame that they have determined, that what they call the term calling half-lives. And we're going to learn how to do half-lives. And one of the most common ones that's used is because carbon is a natural occurring obvious organic compound. Carbon-14 is that particular isotope. It's a relatively young fossil, so it also gives us a lot of accuracy. Okay? So isotopes with longer half-lives for basically older fossils like potassium-40. Okay? So that brings me to, which it didn't give us enough attention to detail, is this right here is what I want to focus on today. And I told everybody yesterday, for instance, that the radioactive dating that we'd be doing, all right, was not enough attention to detail, which I wanted to go into a little bit. All right, so basically, I did the notes for you here, and they're uploaded in.
Please call 4009. Begging God, please call 4009.
Yep, that's one of the things there. So 7th hour just got out at the end of the day here on Monday, and I want to go ahead and make this video. All right, so basically this gives us what you need to know about the history, the who, what, when, where, and why of radioactive dating before I teach you how the actual process works. Okay, so basically the world of radioactivity has extremely useful applications. Particularly, it allows us to determine the age of many different types of material. When using an isotope, which basically is an element with an unusual amount of neutrons within the nucleus, obviously making it heavier or smaller, gives us what we call a radioactive isotope. All right. Carbon-14 is one of the most popular ones. Okay, the first method was invented by this gentleman here, Willard Libby, not until the 1950s. So it's not really that long ago. I mean, post-World War II type era, right in there. He discovered that carbon-14 had a half-life of nearly 6,000 years. Basically, what that meant is the sample. If this baseball was an example of a carbon-14 atom, that in 6,000 years, when this thing began to decay, half of it would disappear in 6,000 years. So that's where the term half-life came up with, all right? So one half-life, if this baseball was representation of a half-life, would take 6,000 years for this baseball to rot away, half of it. Then, at 6,001 to 12,000 years, that other half of that would go away. So every time one cycle of this in carbon-14 goes through a cycle, half of what's there goes away. So that's why half of the half would be 1/4 of the original thing, okay? Which we'll do the simple problems on that too as well. So I just rounded up. The answer is closer to 5,730 years, okay? But for this course, just 6,000 for what we're doing, abbreviated for that. Okay. Moreover, although carbon-14, this is how we get it. This is important to know too. Well, you know, if we're going to learn about something, we might as well know how it comes about. So carbon-14 on the surface of Earth constantly is decaying away. It's also being produced through cosmic rays, which are high-energy photons. Obviously, make sure to define that. Hit the atmosphere, produce neutrons. These neutrons are absorbed by nitrogen, which then immediately emits a proton, creating our carbon-14. So in a quick nutshell, that's how we get carbon-14, okay? So the net effect is basically produces the same rate as things decay. So what it's saying is, right now, all right, the amount of carbon-14 that's decaying in me as an organism is being replaced. So it's a give-take, so it's balanced itself out. So that's why it stays constant. Carbon-14 stays constant in living things, plant and animal, okay? So its level is what they figured, 1/1 trillionth of it. That's the ratio. 10 to the 12th power of ordinary carbon, okay? You don't need to have to do any figure on that, but they did all those calculations for us. So basically, plants absorb the carbon when they breathe in carbon dioxide, so the carbon in plants consists of 1/1 trillionth of C14 as well. We eat plants, okay, and animals that eat plants and animals and so on. So because of that consumption process, that allows the carbon in our bodies to also be 1/1 trillion, okay? So real quick in this little paragraph, you weren't getting in the textbook, is explaining where carbon-14 is and why the cuppeth is always full when it comes to carbon-14, okay? So as long as we eat and breathe, as long as we're alive, okay, carbon always stays at 1/1 trillion. But what happens, I'm just moving the notes up here a little bit. Unfortunately, all living things, when they die, no longer eating or breathing or taking in new carbon-14, but carbon-14 continues to decay. Okay, so this is where that half-lifing or that shelf life or how old something ago lived is when this formula comes into place. So after you've buried something for 6,000 years, like I said, the amount of carbon-14 in your body is reduced to half. Okay, that's the term half-lifing. Just visualize it cutting this baseball in half after 6,000 years. Okay, all right. So by measuring, for example, if you measure that a bone does not have 1/1 trillionth of a carbon, but only 1/8, 1/8, 1/8 of a fraction, okay, then the original part, that means it's gone through 3 half-lives. So think about that. 1/2 times 1/2 times 1/2, 2 times 2 is 4 times 1/8. So that means if I was to cut this thing into 8 equal sections, that's how much of the carbon-14 is left. So we know what every time it halves, it goes through half-life. So we could say it's gone through 3 half-lives. Or what's the total years? Well, if we're just saying 6,000, it's gone through 3 half-lives. 6 times 3 is 18. All right, 18,000 years. Okay, so it's really, if it had gone through another half-life, would have been times 2 again, which would have been 1/16. It would have been 6 times 4 half-lives, 24. So it's a simple process. Remember, every time it goes through a cycle, half of whatever there goes away, and your portions get smaller, like in a pie graph. Okay, 1/2 is 1 half-life. 1/4 would be 2 half-lives. 1/8 would be 3. 4, 1/16. 5, 1/32. 6, 1/64. You get the point. Okay. All right. So, so this method is extremely useful for archaeologists. Current controversies include the question of when, for example, and this is just a cool little trivia question, when did hominids, or when did we occupy North America, humans, okay? So carbon-14 dates would be great if we could get a hold of some of the oldest human fossils located in North America, but unfortunately, they arrived before the last ice age ended. But because of the protected rights of Native Americans, okay, which have sacred areas of which old tribal burial grounds, if you want to look at it that way, are protected, they're unable to exhume the bones to take carbon dating residue from that to see actually how old or how far back those date prior to those ice age. So there's always been, just speculation or guesstimate, but there's no accuracy exactly when the nomadic or when humans migrated into North America, across the Bering Strait and down Canada, and into North America. Okay. So that brings us to that's great if carbon-14 is beneficial with that, but not all isotopes have a long shelf life. Some isotopes are better than others. For example, to get those billions of years and those ancient dinosaurs and things like that, other isotopes. Some isotopes aren't any good. They all organically break down, but some of them break down in seconds. So you can't get any clarification with that. So, for example, potassium-40 is the other flip side of another great isotope that we're going to address and talk about too as well, because it has a really long shelf life. Okay, it decays very, very slow. So basically, K40 is the isotope potassium-40. Means that the total number of neutrons obviously is 40 total. Okay, the half-life of K40 is 1.26 billion years. That's slow. Remember, carbon-14 was 5730. Okay, or we just called it 6,000. This one takes 1.26 billion years. Okay, so when it decays, obviously same things. What it does, it emits electrons, and the remaining of those turns into argon. So they're able to measure the amount of other gases. So the isotopes breaking down are all the same, but different ones have different ways in which they measure them. And I'm just kind of explaining to you a little bit on how they measure that. So for example, this is particularly useful for geologists for rocks. Imagine a volcano blows up, blows all this pyroclastic stuff, all out molten rock. Hits the sea, okay, hardens immediately when it hits the cold water, all right? Because the rocks are hot and molten, traps the gas with inside it. So when the rock solidifies, it initially has no gas trapped inside, but here's the potassium inside. There's a technique they use in which they can abstract it, turns over the decaying, you have the presence of argon gas. Because the rock is solid, the gas cannot escape. So the rock might be trapped in the seafloor sediment, where it also becomes part of a newly formed sediment rock. There might be fossils in around it, okay, or these particular rocks that date to maybe some cataclysmic activity. So the rocks around it, they can radioactive date to help give you an idea of what took place on that particular layer of stuff, right? Just kind of painting this larger picture for you as how all that stuff works. So perhaps, like I said, there's a fossil embedded in that. So you wonder how old the fossil is. So in the same sedimentary rock, geologists notice the rock, you can tell, came from the volcano. So they take it to a lab, they abstract the amount of argon that comes out from this measurement or from this tool that's able to do that. They can tell you how long the rock was formed, all the molten parts. So then obviously knows when the dinosaur bone was laid down. It's a method called potassium argon dating, or potassium-40 dating is fine. Okay. And it gives us the best estimate for the age of ancient fossils. So, knowing that geological time scale in 5.1, where I said don't memorize that, that's how we accurately were able to create that, basically, chapters, if you might want to say, of that stuff. And understand that, giving you two perspectives. Carbon-14, most popular one, which is actually a relatively short half-life to use, but potassium-40 is how we know those things all the way back to the Precambrian time period, the Cambrian explosion, and large cataclysmic activities over the millions of years ago, because of this one that's present from a lot of pyroclastics or eruptions and things of that nature, and it works out real good. So this is the notes over radioactive dating, just understanding a little bit, especially where's carbon-14 come from, how does it break down, how does that decay. I wanted to give you just a little quick explanation, understand that you weren't going to get that from 15.2 out of the book. Okay? And then our next step is learning how to solve problems, if I give them to you, exactly to determine how old various things are. Okay? So that will be then the next as far as hands-on assignment. But I thought I'd go ahead and go through this real quick. It's a one-day little lecture type stuff that you can watch on your own. Obviously, my B groups will be watching this right tomorrow. And without me even talking about it, you can watch it too as well. Okay? All right, I'll get this uploaded this afternoon.